All right, so just, we'll figure out the seminar next week, okay? But I have a great opportunity to have, John East here today, and so, just gonna just have him give a talk today, and then, next week we'll kind of go through logistics and things like that. So the quick logistics that anybody was, few people were asking about 1 or 2 credits. So 1 credit, you just have to show up. 2 credits, you have to, present some presentation, so like 10 to 15 minutes one time. So we'll go over that. It'll be probably later in the quarter. We have a few people that are already lined up for the quarter. So I know you need to know that beforehand. So if you sign up for 2 units, in next week, I'm going to say you have to give a presentation about your research or about something, sometime, halfway through the quarter. Okay.
When's the deadline to sign up?
I think it's Friday. I don't know. You guys know better than I. So whatever that might be, but you should sign up if you. You should sign up for 1 unit. Anybody else that was in my class too, if you were interested in coming to this seminar, you're more than welcome to. So. Great. So, I'm really putting John to work today. Yeah. Sorry. John's just gonna sit down. So I need to get you some food too, so that will come here in a second. Yeah, okay. So it's a really great pleasure to have John here today. Just gave an amazing talk about how to be successful. And now he's going to give a talk about basically history of Silicon Valley. John was there since the beginning days at Fairchild and kind of going through the whole shebang, which you'll hear about, and then CEO of Actel for 20 some years, and now it's just enjoying life and coming every once in a while talking about these sort of things. But an amazing person and amazing stories to share today. So thanks for joining us, John.
You're welcome. You're welcome.
These please.
No, sure this works.
Make sure it's actually included on the slide.
Me, yeah. Is it working or no?
Yeah, just click on the presentation, I think. Abstract.
No, is it working?
Yes. So Ryan knows and you know as well, right? What's the first thing I'm going to do? Yes.
The story.
No, we're going to come out.
And I took the seat this time.
It's Chris, right?
Yes.
So he's a PhD student, really good school. He's clearly a very bright guy, but he has this one little weak spot that you didn't pay enough attention to. Because he knows that he just took the worst seat in the house. And he got here early and took it. Because this is the guy I always pick him. He put his mask on.
Sorry, John. Some people want to watch it remotely. So
It's in the participants menu,
sorry, where is it?
in participant. Yeah, you click on that, and then the invite button.
Yeah. Okay, perfect. Good, yeah.
Hey guys.
Scientists, how many degrees does a scientist need in order to figure out Zoom?
You're doing good help from me. I can never figure that stuff out. I have a grandson that could do it, but he's not here.
Yeah.
wife just got a new electric car with the electric, on the Lexus. And I can figure out how anything works. So we-
Okay, I think we're good.
We had to take our grandson for a ride and he figured it all out.
Okay, sorry, John, go ahead.
All right, not my problem. Let's just see.
You gotta make sure the slide shows the actual, tap on the software.
Man, you know what, man, you would be a killjoy.
Yeah. Buzzkill in your class.
Buzzkill, okay, I didn't.
Learn to do
Consider the wrong question.
The word?
It is not working.
The,
So I'll warn you, Ryan unfortunately knows that you don't, I get going with these stories and sometimes I'll talk too much. So there's some chance that I don't get all the way done, Ryan, and we'll just say, fine, I'll come back and finish it. So that's a picture of the Titanic sinking in 1912. I was a kid, maybe 9 years old. I was 9 years old and I saw the Titanic. Not the one that you've seen, which was made in 2000 or something. This one was made in like 48 or something. But what I was fascinated by was not the ship going down. I was fascinated by the CW, continuous wave radio, or I thought, man, that is really cool. I wonder how that works. Which is kind of strange because we had a television, we had a radio. Those didn't impress me because I'd always been exposed to those. But that was very cool. That caused me to get a ham radio license and then later be a double E. So that's how I got into business. And that's we're now going to start out with how did that thing work that I was so excited about? And it looked like that. Stuff.
Uh-oh.
I don't know what I did. Okay.
Oh, you're back.
So I just had the laser. Let's see. I gotta poke something inside the laser. Okay, this stuff just acts to use a battery to charge up two big capacitors. And there's a little spark gap here. When the capacitor voltage gets high enough, there's a spark that jumped across that. Okay, that was no big deal. But the thing that Hertz did, and he's by the way trying to prove out Maxwell's equations, and he did so successfully. The thing that he did was he put a loop of wire. The wire is about 1 meter long. He just took it and wrapped it around itself, so that it also had a little bitty spark gap. And what he found was, well, anytime he saw a spark here, he also got a spark there, which even today, when I look at it, come on, that can't be, but of course, Maxwell's equations would tell you that was going to happen. So he could do it over a distance of about 1 meter. He thought my job's done. I proved out Maxwell, and he was finished with it. But this guy named Guglielmo Marconi, do I pronounce that right? Guglielmo?
Yeah.
Guglielmo. Guglielmo, okay. Said, hey, I can turn a buck off of this idea, and he went to work on it. And by 1895, he could actually transmit and receive a signal over a distance of about 1 mile. And by 1901, they sent a signal across the Atlantic Ocean to the easternmost part of Canada, a place called St. John's. Or by the way, there is a museum that has the original equipment they used, and it's fascinating. You have a chance to be there. So they now transmit a signal across the Atlantic Ocean, which was fantastic. And the first real use for it was cruise ships, any kind of ships. So all the ships got this kludgy setup to do Morse code kinds of transmissions with. Now, let's just say that there had been a body, a very august body of super scientists there when he sent that signal across the ocean. So let's put on that panel Werner Heisenberg, and we'll put Albert Einstein, and we'll put Max Planck, and then of course we have to have Ryan. Let's see what they would have said. Heisenberg would have said, hey, I've taught you 100 times. If you know exactly where something happens, you don't have any idea what the momentum is. How many times do I have to tell you that? Einstein picked it up from there and said, well, you're right, but what I've told you 100 times is it's a 4-vector world. It's space-time. And what you should be saying is, if you know exactly when something happened, you have no idea what the energy was. Same state, right, in 4 vectors. Max Planck then chipped in with, well, I've taught you guys 100 times that the frequency is equal to the energy divided by this constant that I very cleverly named the Planck constant. So what you should be saying is, if you know exactly when it happened, you have no idea what the frequency was. And by the way, we do know exactly when this happened because the spark happened at a very precise instant. So generally what's going on here is we're shooting off photons in every possible direction at every possible frequency. At which time Brian observed, wow, you guys have invented ultra wideband. And that was the first radio. You know, I made up the panel, but that's basically what came down. That was the beginning of it. Now, it was a fact, and I'll talk a little more about it in a minute, but it was a fact that ultra wideband or the spark radio sucked. And it needed something to kickstart it. And the thing that came along to later kickstart it was one of three of the, in my mind, most important inventions, the ones that changed the world the most in history, and that was the vacuum tube. Now, if I have more time and a different kind of audience, I ask people to raise their hand if they know what that is. I don't tell them it's a vacuum tube, and I bet I wouldn't get better than half of them here. But that was the early transistor. It wasn't a transistor, but it was a three-terminal device. And if you look at a schematic, it has transistors in it. Mental, you take out the transistor, stick in the tube, kind of works the same way, except the transistor is about 1 billion times better in speed and in power. But that's what people use to improve it. It hung around for maybe 15 years, and people were doing a little tinkering here, a little tinkering there, but they didn't figure out a real use for it until about 1920, when a guy named Reginald Fessenden came along with what I'm calling here Fessenden modulation. So this would be a good quiz to give you on a test, but I don't give tests, so you don't have to worry about me. Parse that circuit, tell me what's going on. But I'll do you a favor, I'll tell you what's going on. Green oval there, that's a crystal oscillator. You could have looked at it and figured it out, because down here you have a crystal, so you'd figure that's a crystal oscillator. Now Fessenden did not invent that. Somebody else had done it. They didn't really know what to do with it, but that had already been invented. Then here in the red oval, that's just an amplifier. Over to the left where it says line audio in, hooked a microphone up to that. And all this thing did was amplify the microphone signal. And Fessenden didn't invent that either. So what did Fessenden invent? You ready for this? Fessenden invented that. There's a message there somewhere that sometimes the best inventions are the most obvious. But what he had done, of course, was to modulate the amplitude of that oscillator signal with the signal coming out of the microphone, thereby creating an amplitude modulated radio. Now, had he been smart, he would have named it Fessenden modulation. He would have ended up rich, powerful, famous. He didn't. He named it amplitude modulation. So I'll bet you none of you in here had ever heard of Fessenden until I presented him. But he's the guy that made it happen. And this radio was cool radio because it wasn't did stuff. You could have voice, you could have music. It was the real deal. And people immediately started prognosticating that, gee, it won't be long and there'll be one in everybody's home. There were a couple of problems with that, so it actually took that 25 or 30 years to happen. The first problem was those radios were big and cumbersome and expensive. That's a radio. That was one of the early radios. And I've actually heard one of these. Sound is just dreadful, but it does work. And people, if they had the money, which most did not, would have been happy to have one of these in their house, except for one reason, and that is the wideband stuff that Ryan named. It was still out there. So what's going to happen if you've got this AM radio and a whole bunch of wideband transmitters all around it? Can't hear anything. So the world got together in some kind of conference that I once knew the name of and I've forgotten. And they decided we got to do something about this. AM is a really good deal, but nobody can use it because of wideband. And so the fate of wideband was it was banned by international accord, not allowed anymore. Came back sort of recently, but with the power of a mask at very, 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 very low levels. So it doesn't do the damage it did before. But for 30, 40 years, something like that, there was no wideband anymore. Now, you're saying, well, this is fascinating, or maybe you're not saying that. Maybe you're saying this is boring because, radio, come on, what's that? I want to talk about digital. I want to talk about computation and DSP and security and all the stuff that's going on today, and all you're talking about is stupid white man radios. Well, there's a reason that I haven't talked about that yet, and this will exemplify the reason. That's Tom Watson. He was the CEO of IBM, who, in my youth, dominated the computer business. IBM was bigger than all the other manufacturers of computers added up. There were 7 others, RCA, GE, Siemens, I forget, and they had a name for the insignificant 7 or something like that. I can't remember, but IBM was bigger than all of them. So they were Mr. Computer, IBM was. However, in 1943, CEO of IBM made a statement. I think there is a world market for about 5 computers, and we're not going into it. You think we're stupid? We're going to continue making our typewriters, which is what they made at the time. And they rejected the computer market. Now, is he stupid? Well, here's the wrong tense. Was he? I don't think so. Let's look at why. He made that statement in 43, and as he was making the statement, they were building the world's first real computer. It was built at the University of Pennsylvania with jillions of scientists and tons of money and what have you. And that's a shot of the world's first real computer. There are a lot of different things that can kind of lay claim to it, but I think this is the one that really deserves the praise, the first computer. That ENIAC came out in 1946. Pretty big, powerful computer, except that it was less powerful than your pocket calculator. Now, I'm not talking about your phone, and phones, heavy duty stuff. I'm talking about your pocket calculator. This was not that powerful. Interesting thing to look at is the backplane. Let's see what, if we go back behind one of these things, what we see. A couple of ladies. Anybody know what those ladies are doing? Yes.
Programming it?
Yes, it's very good. Those women are computer programmers. You program a computer by running jumper lines from one point to another. It was viewed at the time that women were the very best programmers. Now you're thinking women are better at everything. What's the news there? But you didn't say it. But you're the one that got the answer. Good for you. So that computer, again, was about as powerful, not quite as your pocket calculator, but mean time between failure of about 15 minutes. And it used the power of a small city, because vacuum tubes were not low power. So pretty shabby, and that's why the VP or the CEO of IBM would say, well, we're not going to fool with that. That's an academic thing. Okay, 1947, the second really major invention came. The first one was the vacuum tube, the second was the transistor. William Shockley was the boss of a group of 3 people. John Bardeen and Walter Brattain actually were the ones that first figured it out. Shockley took the credit. And in fact, he probably deserved most of the credit because he was the smartest guy and he was the one that put him on the path. He was an absolutely brilliant guy. 1947, invented the transistor. If you looked at the transistor today, you wouldn't be able to figure out it was a transistor because it was neither bipolar nor MOS nor JFET nor anything. It was what they call a contact transistor. And if you look at it, you still can't figure out how it works, but it did. They were able to amplify a signal with it. Shockley, he believed, and everyone that knew him agreed with, might have been the smartest human being to ever have been born. He was really, really bright. He later went on, and I'll show you, hired brilliant, brilliant people from brilliant universities. And he actually was so smart that each and every one of them said, I can't keep up with Shockley. He's a really smart guy. He had some personality problems we'll talk about later. But eventually he decided that, okay, I am the smartest guy in the world. I do more about solid state physics. I don't think they called it that then. I know more about transistors than anybody else in the world. Transistor is good. Other companies are starting to make them. I'm going to open up my own company. I'm going to make transistors and I'm going to do it better than anybody else. So he moved from Bell Telephone Laboratories, which is in New Jersey, where he made the invention, or they made the invention, to where his mother lived, because he wanted to be near his mother as she was getting older, and his mother lived in Palo Alto. So he moved to Palo Alto, figured out a way to get money, and if I had more time, I'd talk about that, because getting money is what startups are all about and was back then, but I don't have enough time. One way or the other, he figured out a way to get money, and he opened up Shockley Semiconductor, which was the first silicon in Silicon Valley. By the way, most transistors then were made of germanium, but he understood properly that that wasn't the right way to do it. But had he looked at it the other way, it might be called Germanium Valley today, but it is not. First silicon in Silicon Valley. Now that's a shot of a lunch at a famous restaurant, but I won't go through why it was famous. It's gone now. But in 1956, they celebrated Shockley winning the Nobel Prize, which is a big deal. It's 9 years after he made the invention, but that's typically what it takes for a Nobel Prize. So that was the celebration that, yeah, people recognize this is an important invention. That's a picture of Shockley. I met him actually later than that, and when I met him, he looked younger than that. That one makes him look. I don't think it's a good shot of him. I think he looked a little younger. That's a picture of Bob Noyce. We're going to talk about him more in just a minute. That's a picture of Gordon Moore. We're going to talk more about him in just a minute. They all work together at Shockley Semiconductor. Now, Shockley had numerous personality projects. He, I guess the essence of them was he hired the very brightest people in the world. He hired only from the very best schools, so he might have come here, except I don't think this was rock and rolling back then. But his typical guys were MIT, Stanford, Caltech, Berkeley. That's where he went. And he got not just the PhDs, but he knew all the profs well because he was akin to God then, having invented the transistor. And so he got the profs to tell him the very, very, very best PhDs from the very, very best schools. And that's who joined him and worked for him. And then he treated him like dog meat. What was the term I learned today? The buzzkill?
Buzzkill, yeah.
Treated him like buzzkill. Well, nobody likes being treated like buzzkill, but if you've got an IQ of 200 and we're the very best student at UC San Diego, and the guy's treating you like some little kid, you don't like that. I did, in fact, have the opportunity to meet Shockley just one time. And it's kind of interesting. He was not a big guy. I might have been a foot taller than him, maybe not quite. But he had that strong handshake and he looked you right in the eye. He's kind of scary. He intimidated me. It's just the kind of guy he was. He intimidated all of his people. And eventually they decided, I can't take it anymore. I'm leaving. And a bunch of them en masse left him. And that bunch that left was referred to as the Traitors' Eight. So they left him and again had to go through the raising money. I'll come back next year and tell you about the money raising, but I won't now. And they formed Fairchild Semiconductor, which was the daddy of integrated circuits in Silicon Valley. People don't know that much about it now, but it's where it all happened. So let's look at these people. That's Bob Noyce. I'm going to threaten you. I was going to tell you more about him in a minute. That's Gordon Moore again. And that's a guy named Gene Kleiner. Now, right away, I'm going to talk about the first two guys. Kleiner, you're going to say, who is that? I don't know him. But remember the name because we're going to come back to him. He'll turn out to be an important guy. So they formed Fairchild Semiconductor, and there's the original family tree of silicon in Silicon Valley. It started with Shockley Semiconductor, and then went to Fairchild because of the Traitors' Eight. That's where it all started. Fairchild was a famous company. Why were they a famous company? There was a big problem that everybody knew had to be solved, and they were the first ones to solve it. So the problem was called the wire problem, which a long time ago, everybody knew what the wire problem was. Raise your hand if you know what the wire problem was. Yeah. One, got one. Okay, here's the wire problem. Let's say that you're designing a gate. In the earlier lecture, I said that was what I did. I designed gates. And let's just say, for the heck of it, that to design a good gate took 10 wires. I made that up. I don't know how many it takes, but it takes 10 wires. So let's say that then we move forward and say, no, I don't want you to design a gate. I want you to design 2 gates. How many wires does that take?
Okay.
Well, 10 to design this gate, 10 to design that gate. You're damn good if you don't hook them up. So, and typically two gates you'd make a latch out of, right? So I gotta have two wires to hook up, head one to the tail of the other, et cetera. So no, it's not linear. The number of wires required goes up exponentially with the number of transistors. And you'd say, well, okay, now I'm only at 22, but okay, now I say, okay, let's make a full flip-flop. Now we have 4 gates. It's not 44, it's 50, some number like that. There used to be big arguments. It used to be actually a matter of scientific interest in universities to figure out what that exponent was. And there was something that was a cousin of a rinse rule.
Rinse rule, yeah.
Rinse rule. So now I don't want to bother with that stuff now. If I ever understood it, I didn't anyway. But that was important. But what the importance of it was is this. It didn't take long to figure out a way to make a transistor very, very, very small. So relatively early on, you could say, you know what, I could take 1 million of those transistors and get them in area the size of a baseball. It's not a big deal. But 1 million transistors probably takes 1 billion copper wires soldered at both ends insulated. 1 billion copper wires soldered at both ends insulated is crazy. You couldn't get that many good solder joints if you ever had to solder. You know, it's harder than it looks. Too much space. Thing would be the size of the moon. The wires would be infinitely long. The delays, so it just wasn't workable. So in those days, people didn't even consider big digital devices, and most of the use of transistors remained televisions, radios, radar, that sort of stuff. So they had to solve the wire problem, and along came Bob Noyce. He invented the integrated circuit. There's you all know what an integrated circuit is. I don't have to describe to you, but the most important part of an integrated circuit, if you look at it vis-a-vis the wire problem, is you've got all the wire you need there. In fact, just one layer of wire these days might have several billion, maybe 1 trillion connections. And if you need more than that, you put another layer on. You need more than you put another layer on. I think they're up to like 20 layers now. Is that and there's no limit there. They planarize after every one of them, so there's nothing going to the dogs when you put new ones on. So hopefully before I die, they'll be putting 100 layers on there. Solve the wire problem, and that was the biggest thing about the invention of the IC wire problem. The place they invented that, if you ever get up to the Bay Area, there's a street called San Antonio. And so you're driving up and down 101, you see San Antonio Road. You turn left on San Antonio Road and head towards the mountains, not towards the bay. And the first major intersection you run into is called Charleston. So now I'm in my car, I'm driving towards downtown Mountain View. I'm on San Antonio. Here comes Charleston. Right there is the building where he invented it. And in front of it is a historical landmark plaque. And the historical landmark plaque lets you see that, yeah, what he invented then is what we do today, only we do 1 trillion times more than we did then. So it was quite an invention. Now, there was another guy, a Texan named Jack Kilby, who I knew and was a very nice man, who also claimed to invent the integrated circuit. And he was the first to get more than one transistor on the same substrate, but he didn't have an answer to the wire problem. So whereas I loved Kilby, a very, very, very good man, the credit for the invention that moved us forward goes to Noyce. That's a picture of the first integrated circuit. And again, if we had more time, I'll take you through that, because when I first started at Fairchild in 1968, I was a product engineer of that family. It's called the Micrologic family. It's the first family of integrated circuits. But this is your lucky day. I don't have time, so I'm not going to take you through. So the wire problem now being solved, now you can start thinking about, okay, let's make some of this big stuff. We'll let the digital revolution begin. So we have to have a baseline. This is the baseline for where we started. It was called the RAMAC or RAMAC. I never knew how people pronounced it. But it was the last vacuum tube computer, because IBM did actually start making computers. This was announced in maybe 55 or 6 or 7, something like that. It was a vacuum tube computer. Had about the same power as the ENIAC, which I showed you earlier. It wasn't really more powerful, but it had one huge advantage, aside from being much smaller and lower power. And he's pointed to the huge advantage. That was the storage system. The RAMAC could actually store 5 megabytes of data. Unbelievable number at the time. How do they do that? Well, you can't really store 5 megabytes. What they did is they stored 100 kilobytes 50 times. So disk drive, they're just being invented. That's a stack of 50 disks. Each one had the capacity of 100 kilobytes. I had a friend who worked at IBM at the time, and he was saying that was big time, 100 kilobytes on a disk. Of course, it wasn't 1 foot disk, but that was big time. So should you be the type that likes to listen to music when you run, you could have in fact gotten a big truck, put that computer on the truck, wife drives the truck, you run along, right? You need a heck of an extension cord. And by the way, the output of those computers was always in what they called IBM cards. Has anybody ever heard of an IBM card? So you couldn't really listen to music, but you could have read it on the IBM card. It would take about 100,000 IBM cards for the song that you like, by the way. So that was the status back when the integrated circuit was invented. Now, we talked about Gordon Moore. We said that he was one of the traders. He worked at Fairchild, and when he was there, he wrote a paper for electronic design. Sometimes I get that confused. There's somebody with the same title, but I believe it was electronic design. And the title of the paper was "Cramming More Components onto an Integrated Circuit." So I'm not making that up. If you Google that, you can come up with the actual original article. And basically what he said in that article was, wow, if you plot this thing on a semi-log scale, you can see that we're doubling the capacity every year. And I don't see that stopping for the next 10 years. So what he projected was by 1975, we would actually be making circuits with 64,000 components on them. Now, had you been working in the industry at the time, you would have thought, man, he's a Berkeley guy smoking those funny cigarettes. It's not going to happen. It's not going to happen. But that's what he projected. And now it's fun. People, all these wise people that never really understood it when he was writing it, but now they understand all about it. They want to tell you, oh, it's going to go on forever. No, it's not going to go on. It's going to taper off. Oh, it's already dead, et cetera, et cetera. I mean, it's sort of easy. Just plot this thing on log. It goes on forever. You never stop making progress. It just slows down over time. Exponential things have to, right? So he was a visionary. He died, by the way, about a year ago, a little less than that. Nicest man in the world. Well, it was a time for nice. I'm fortunate enough to have known all these people. I knew Noyce and I knew Moore, and they were just the nicest people in the world. Moore really shy, didn't have much to say. He wouldn't brag on himself. Noyce was he was an incredible guy. He liked everybody. Everybody liked him. He could have been president of the United States. He could have been a great politician. He was just a super smart, super capable, super likable guy. But he died 1989, I think. It was a long time ago. Unfortunately, the world is less in place than it was not. So that's Moore's Law. Now, 1 year after Moore's Law, 2 guys left Fairchild. And it's going to seem to me for a minute like I'm going off the topic. I'm not really going off the topic. You just aren't going to see why I'm not for another few slides. But the 2 guys that left Fairchild were Don Valentine, who'd been running sales and marketing at Fairchild. And he left Fairchild to go to National Semiconductor. Neither of those companies are around anymore, but there was a time they were both major figures in Silicon Valley. The other one was Pierre Lamont, who ran all of engineering and manufacturing. So between the 2 of them, they were pretty capable people, right? Sales, marketing, engineering, manufacturing. They had the whole deal. National hired them. They went to National, hurt Fairchild a lot. What's the end of that story? Well, you're not going to know for a while, but I'm going to leave, come back to them. So you got to remember who they are. So integrated circuits have been invented, and Gordon Moore had said, oh, you're going to get 64,000 on a single chip and all that sort of stuff. But there were problems. In the earlier class, I told Ryan, threatened him sort of with, the last circuit I actually designed was a quad 2-input TTL NAND gate. And you'd think, well, design a NAND gate, but then it was big time. I felt proud. I told my wife, man, I designed a NAND gate. Of course, she didn't know what that was, but I told her it's very important to have done. You wouldn't think that much of it today, designing a NAND gate. But that was an AND gate. Okay, fine, John, it's terrific. You notice bipolar transistors, not MOS, because MOS didn't work at the time. But what's the problem? Well, if you whip out your iPhone, I, by the way, have a 6, which my wife says, you moron, you gotta get a real phone, but whatever one you have. If you whip it out, happen to get the schematic of what's going on inside, the actual gate level schematic, which I don't know, people even make those anymore. But if they did make a gate level schematic, and then you rebuilt it using TTL gates, you'd have any number of problems, but my favorite problem is the power required by that phone would be about the power of one full-size nuclear power plant. So should you take the phone that you designed and built, and you wanna bring it from home, wherever that is, to school, you would need to bring that power plant with you, or a very long extension cord. Needless to say, it's still a problem when you come to these largely integrated circuits you're talking about today. There was a different problem as well, it dealt with storage. I'm gonna have more time and give the quiz, how many people have any idea what that is? I won't, well, how many people have any idea what that is? One, yeah, a couple. All right, you're not gonna believe this, actually, it's so archaic. That was a memory. These things are just little donuts made of iron, so they're magnetic. And you put an array of them, just as I showed you there, and you'd run 3 wires through each one. One up like this, one up like that. No, I did that wrong. Horizontal, a vertical, and a 45 degree. And we actually had to study this when I went to school. It was a shame to waste brain cells doing that. But you could make a memory that way. You'd magnetize the thing to be either north or south pole, and then you'd sense it with a triangular line. Which way is it? You had to actually destroy it in order to sense it, and then you had to rewrite it. What a mess. But that's the way memory was done until about 1975. What's the problem with that? Well, only the obvious problem. But that is a picture of an installation of additional memory in a computer. When I was a student at Berkeley, I actually had a job in the computer room, and we had 8K bytes of core memory. And you'd say, 8K bytes, you can't do anything with that. Well, the whole trick in those days was figuring out how to write a program so you could do something. That was the hard part. But they eventually said, well, 8K is not enough. We're going to add 32K, this monster amount of memory to it. And that, I wish I had taken that picture. I didn't, but I found it on the web. That is a picture of the installation of 32K bytes of memory. So you think, okay, in today's terms, the memory on my iPhone, let me do the math. Well, it turns out it would be about the size of the Great Pyramid of Egypt. So we've got, in order to take your phone to work or to school, you need to bring a nuclear power plant and the Pyramid of Egypt. Well, it's not going to work. So a lot of work had to be done to get to the place we are. But at least by then, people started to think, well, we can do it. We can do it. We start working. Now, it's the same shot you saw before. Those are the founders of Fairchild Semiconductor. Those are the Traders 8, in fact. They are the ones that got the Valley in the mode of doing startups, because they all realized that integrated circuit was going to be really big, and there was going to be a lot of money to be made, and they realized that there weren't many people in the world who knew how to do it, but they did. So they all broke off and did startup after startup after startup. Some of them did as many as 6 startups. Only 2 of them were limited to a single startup, and we'll talk about them in a minute. But putting those 2 aside, everybody else did at least 2 startups, and some of them did 6, 8. They just kept doing startups, and so they do a startup, get it going. We even do another startup, get it going. We even do another startup, getting going. The trick at the time was raising money. We're going to talk about that in a minute. But it got the Valley where it is today, which is startup. It's all anybody cares about. And it's actually worked well for the United States. So they all did their startups. The 2 that I threatened to talk about a little more, though, were Noyce and Moore. They only did 1 more startup, and that startup was Intel. So they founded Intel in 1968. And that's just as an aside, 1 year later, a guy named Jerry Sanders formed AMD. And you'll notice that even today, they're still doing bitter rivalry between the 2 companies. I was an AMD guy, so I was supposed to hate Intel, but I take my hat off to Intel. They really made it happen, because their first product, which came out about halfway through 1969, was a static memory. Now, other people were trying to make static memories, But the typical static memory at the time was maybe 64 bits. And Intel actually put out a 256 bit static memory that actually worked and got decent yield. So they didn't invent the static memory, the SRAM, but they were the ones that really got it going. But after that, they invented the DRAM. A lot of other people working on it, but you got to give credit to somebody that invented the DRAM. Then they invented the floating gate memory. At the time it was called EEPROM, then it became EEPROM, now it's flash, and now there are a whole bunch of memories that I can't even keep track of anymore, but this was the first actual mass memory that worked. Anybody know, this appears to be glass where you can actually see the integrated circuit in there. Why would that be? Anybody know? Okay,
I believe it's still, if it's like similar to that came out for ultraviolet.
yeah, that's right, that's right. You couldn't electrically erase it. And they, at first, they just put the product out in a regular plastic package and you could program it once. Make a ROM out of it, but people realized, oh, I'd like to be able to erase it and reprogram it. And they figured out, I can erase it if I expose the charged cells to ultraviolet, but I gotta be able to get the ultraviolet in it. So for a decade, you could find these things where I liked them because you could actually look in and see the integrated circuit. And the people that designed the circuit, they'd buy hundreds of them and send them to all their uncles and aunts, and, you know, I designed that sucker and you can see it. Of course, those days are gone. And then they also invented the microprocessor. Again, a lot of other people working at it, but the first one actually come out commercially that worked, people were using 4004. So you'd say Intel, let's see, really the first SRAM, first DRAM, first flash, first microprocessor. They get some credit. They get some credit. Now everybody's pounding on them. They're getting beaten by this, that, and the other. I don't know. I tend to still give them credit. They changed the world. Now, I threatened you earlier was coming back to when is the deadline for stop?
15.
15, okay. We're coming back to Gene Kleiner. Kleiner was one of the Traders 8. And I told you, all the Traders 8 went out and started any number of new companies. And well, Kleiner did as well. He participated in founding Amelco. Actually, 4 of the Traders 8 did Amelco, and then they all split out. Each one had their own. But he did Amelco, but then he left Amelco. And the thing about him was his father was a banker. There wasn't really such a thing as an investment bank at the time. There weren't such things as venture capitalists at the time. But he understood the equation, which was, wow, we've got startups everywhere, and the one thing they all need is money. And Kleiner's father was a banker. He knew where to go to get money, and he taught Kleiner that. So Kleiner's second startup was not an integrated circuit company, whereas all the others did IC companies. Kleiner started a VC company. Now, again, with more time, there was a guy that was predated him, but I just don't have time to talk about it. So for today, we'll leave. He was the first real VC in the Valley, along with the other 2 guys that I was threatening to come back to, John Valentine and Pierre Lamont. Now, Jared, by the way, is still alive, and Ryan has a favorite company called Security. Pierre and I were on the board of directors of Security for a while. We were still calling it Tortuga at the time. And he's about 90 years old, but he's sharp as a tack. Now, again, I've oversimplified. Valentine had a partner, I haven't told you his name. Pierre came later. Don't have time to get into all the details, but the big picture that you just saw is the first 2 significant major lasting VC companies were Kleiner Perkins, founded by Gene Kleiner, one of the Traders 8, and Sequoia, founded by Valentine and later Pierre Lamont, early Fairchild people that left and went to National. So people always think, well, it was the venture community that put the Silicon Valley integrated circuit companies on the map. And it was, that's right. But it was the semiconductor companies that put the VCs on the map. So the symbiotic relationship worked really well for everybody. Kleiner Perkins, Sequoia Capital are still there. They're among the biggest investors. But don't try to get money from them, man. It's like act of Congress to get money from them. So they started out by saying, okay, we can get money. There are all these integrated circuit startup companies around. I'm going to fund them and get rich. But that only lasted a couple of years. And eventually they said, well, you know what? The real money is not to be made on semiconductor companies because semiconductor companies are capital intensive. In those days, if you wanted to start a semiconductor company, you needed a fab. And even in those days, fabs cost a lot. So there was a lot of capital involved. But the semiconductor companies were enabling all these new different wild things that nobody would have thought of. And those ended up having bigger markets because the closer you get to the world population as a customer, the bigger your market is. If you're selling an IC to 10 computer companies, that's a pretty good market. But if you're selling a computer to everybody that's in the world, that's a big market. So the VCs, particularly the ones I just mentioned, realize I'm not going to do this stuff anymore. Integrated circuit funding is a waste. I'm going to fund the people that are enabled by what the integrated circuit people did. And now, 10 minutes ago, but I'm going to get there. So among a zillion startups, and this history is fascinating. There's a good book, in fact, called The Power Law. It's the history of venture capitalists. But it's fascinating history with companies you've heard of. But the one that I kind of like the most is Apple, formed in 1976 by two guys that didn't even have degrees yet. Wozniak went back later and got one job, never got one. But of course, they changed the world. And who was that funded by? Sequoia and Klein Perkins. 1998. Now, I've gone through a period where I knew everybody that I was talking about, including jocks in particular, like I'm now going to get into a window where these guys are too much big shots for me. I haven't met them. I've never met Page or Brin, but boy, they really changed the world. You're not old enough to really remember, but when the web first was around, there were search engines, but when you searched, you never got what you wanted. It's some ragtag. What is that? It's not what I wanted. You'd search and search and search, somebody couldn't find it. They were the ones that figured out how to know what you really wanted and to give it to you. So the minute you laid your eyes on your first Google search, oh my God, they're going to be wonderful. And they, in fact, were wonderful. Who invested in it? Klein Perkins, Sequoia. Now, 1997, a company named TSMC was formed. TSMC, you're all aware of today because they are the world's largest manufacturer of integrated circuits. I think Samsung is second these days. But their gig was this. It's too hard to know everything that you need to know to be a total semiconductor person. And in fact, that's where Intel first went astray. They were working on being the very best at processing and the very best at computing and the very best at one or two other things. And it's just too much. It's too complicated. So TSMC said, I'm going to take this processing and wafer fabrication off the table. You don't need to worry about that. You just design good circuits, figure out what the world wants, design those circuits. I'll make them for you. That way you can focus on what matters. And when I first heard about it, I thought that's stupid. Everybody knows every fab or every semiconductor company has to have their own fab. I was, of course, dead wrong. The growth in TSMC has been shocking. And that's pretty much the way everybody does it today. This, by the way, shocks me to show it. That's a fab today. First thing you think about it is how big it was, because the fabs back in my day were much smaller than. But the more important thing is there's nobody in there. There's nobody in there. And in my day, it was people swarming all over the place, trying to figure out what was wrong and fix it. And of course, the people swarming all over caused particle counts to go up, et cetera, et cetera, et cetera. So, boy, it's all automated. This is one of the lithography machines. Anybody know what the most recent costs? It's nano aperture, it's an extreme ultraviolet, small aperture. Nobody knows what they cost? $300 million for one of them. Now you notice they go down as far as you can see. So the message there is if you want to build your own fab, bring your checkbook. It's an expensive thing. And because of that, there are really only not even a half dozen customers that really try to do it anymore. It's pretty much all done. May or may not be a good thing for the US. It's a different topic, though. Won't get into it. In 1985, I hired, although I didn't know I had done this, I hired a new graduate of Oregon State, I forget. And he came to work for me. I was the VP, so we had VP, director, blah, 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 blah. But I shake hands with the new kids when they come in and pat them on the back and whatever. Well, one of them we hired was was, you get old, you don't, Jensen Huang. So I actually lay claim now, who's Jensen Huang? Jensen Huang founded NVIDIA, which is now the biggest semiconductor company in the world with respect to valuation, $2 trillion, I think. And how did he do it? Well, he did it by not making his own wafers. He did it by using TSMC. So the coming along of TSMC and the good kicks that they got out of the companies that use them put semiconductors back on the market, or on the VC radar anyway. So should you be a semiconductor company now, you can actually get funded, although it's never easy, but you can't get funded again. Whereas we spent 10, 15 years for semiconductors, I don't want to do it. But now they're rocking and rolling. And I'm gonna get them just in time, although I've been talking too fast. So a little tour through the kind of sort of recent history. First PC really was the Apple, but the one that really took the world by storm came out in 1991 was the IBM PC. And I have a chapter about that in the book I gave you. When it hit the market, it had the name IBM behind it, so people thought it's a real thing, whereas people thought the Apple was like a toy. And companies started buying this like crazy. So the sales just zoomed. These things were sold left and right, and I actually bought one. I have one today. Someday I'm going to dig it out of the box and hope it still works. But it was childish compared to anything you can do today. The chip that I used, the microprocessor that I used, was an 8088, which was an 8-bit version of a 16-bit processor for reasons that you'd find interesting, but I don't have time to get into. But that sounds so. It had 29,000 transistors. Now today that sounds trivial to you, but that was still the time when we designed circuits transistor at a time. You would never think of doing that today, but with the exception of big blanks of memory, you don't have to put every transistor in, but mostly the design was done transistor by transistor. So it was thought, oh my Lord, that was as big as you're ever going to get by doing today's style design, and in fact it was. Then Mac sort of one-upped the IBM PC in 1984 when they put out the Mac, and Apple one-upped them when they put out the Mac, because the Mac had the mouse. The IBM, they still had to do command line kind of entry, and it was sort of complicated. The mouse made things easy. So this then took the world by storm as well. And that was a Motorola processor, 75,000 transistors. I'm now going to fast forward to the Apple M1, which got announced, I think, 3 years ago. 57 billion transistors. Of course, they do their own designs. They got a huge design outfit. But my favorite of all is the Cerebrus chip, which I believe is the one that when you do ChatGPT, you're using. This has 1 trillion transistors. I have a hard time even saying that because to me, 1 million is still a lot, and 1 billion is, and I don't know how you do that. And 1 trillion is hypothetical on me, but in fact, that's what it has, 1 trillion transistors. The baseball is just to show you the size. All the integrated circuit fab people looking at it say, yeah, it's clearly cheating because it uses wafer scale integration. Yeah, it does, but whatever. It's got 1 trillion transistors and it works. So I look at that and think, I can't believe that we've gone from the place where when I started, some days we couldn't make 1 transistor to, wow, now we can make 1 trillion. But I have a friend who's a stealth level startup guy. I can't mention his name or the startup, but he's doing AI. And I was talking to him about this Cerebrus chip. What do you think? That's got to be, they had into all of this. And he said, John, they ain't seen nothing yet. So they're out there topping that. I don't know how they're going to do it, but they are doing it. And I'm 1 minute early, but I've never talked that fast. Have to sit down.
Yeah, I've worked John very hard today, so I don't have any questions for John. And him as well, eating water.
They clearly were fascinated.
Yeah.
Yes.
It's kind of the thing that surprised you the most out of technology that happened last or in your life.
What surprised me the most? Geez. Well, I was a bunch of things, and I talked about some today. Number one, I was a product engineer when I started in 1968. And the R&D people were always way ahead of the real products. So when I first saw Moore's Law, I probably didn't see it until 1970, I don't remember the exact time, but anyway, we were trying to make gates and multiplexes and flip-flops, and the yield was pretty close to zero. And this weirdo says, 5-6 years from now, we're gonna be able to make 64,000. And I thought, that isn't gonna happen. So then to get what we got today, I still don't believe it. Next big surprise, when I first saw the Intel DRAM, you all know how DRAMs work. I'm not sure I know how they work with them. You got a single cell there with low capacitance on it, and Lord help that the charge doesn't leak off of that capacitor. Well, you want to read it, you get a quick reading of it, but then you got to come back around and refresh it in a hurry. And in fact, you got to keep refreshing it. Actually, if you read it, you have to reread it, right? But even if you don't read it, you got to refresh it. And all this depends on the charge stays on the capacitor. Well, the number one yield problem in the day was leak. When we get a run out of fab and the yield was zero, and it happened a lot more than we wished it would, you'd look at the run and almost all of it was a leakage. So I thought, these guys are out of their minds. The first DRAM was a 1K, but the meters afterward announced a 4 and started talking about a 16. I thought, these guys are out of their minds. Leakage will prevent that from ever happening. Then another one would, okay, you're wishing you hadn't asked this, but the last one was, it was a long period of time where people talked about the 1 micron barrier. When you started getting down to 1 micron, you started getting short channel effects, you started getting a lot of serious problems with respect to simulating the thing. You started getting hot electrons, you started getting all the evil stuff that might affect you. And for a long time, people were saying, and by the way, the lithography seemed impossible at the time to make things that small that were good. So it was thought for a long time, no, there is a barrier, there is 1 micron, we're gonna get down to that. And perversely enough, once we got through 1 micron, the improvements started coming faster, not slower. So I retired, and when I retired, 32 microns was the technology. And it was only 12, 13 years ago, something like that. They're making 2 microns. Okay, forgive me. Thank you for not correcting me right away. 2 nanometers, right? And they're getting a good deal with trillion transistor chips. So all those things just blow me away. It just surprised to me that all the progress that has been made did get made. And I take credit for none of it, except for being there watching it. I wasn't the one that did any of that stuff, but collectively, those guys and gals, they changed the world. Good work. And you're gonna be the one that changes it over the next decade. So what it works. The old farts of 45 or so, they're quitting, you're taking them.
When do you think Moore's Law will end?
I think it's log and just goes on forever. So it slows down, never stops.
What do you think the next watershed blocker is? The 1 micron barrier of today? What's the thing that, like, when we finally crack that, we're gonna have a nice little exponential explosion again?
Well, to begin with, I'm feeling like we're still in the exponential explosion. So ride it. But I'm just gonna expose my ignorance. I used to tell people that this thing is gonna limit when the dielectric, the gate dielectric is a couple of molecules thick. Because there ain't no thinner than a couple of molecules, okay? That's wrong. They figured out new dielectrics with higher dielectric constants, and I don't even know what they do today. How do they do that? You couldn't do 2 nanometer with anything that I'm familiar with, but they do it. So, but whatever it is, it deals with lithography. The other stuff, it's kind of linear. You can always implant, but the lithography, I'm shocked at what they do and how they do it. And as you've seen, it's not getting any cheaper. We used to call it an aligner. At Fairchild, it was an aligner. That's what you did the lithography with. You had a mask, and you had a wafer. You put the wafer in there, hits a pedal, that comes down on the wafer where they contact, shoots some light through there. It wasn't even a special frequency. Now you were aligned. The liner costs $2,000. So I just told you, today's a liner, $300 million. So if there's a limiter, since these things tend to go exponentially, yeah, maybe we can go from 2 nanometer to 1 or to 750, no, it'd be 75, no, 7 angstroms, that's what it would be. Maybe we can do that, but maybe that aligner is not 300 million, maybe it's 12 billion. Might be, so that might be a thing. But you know, if I could really answer your question, I wouldn't be here, I'd be investing in stock.
Actually like to add a comment, fascinating story, I've been in the industry, maybe started 5 years after you did, so.
Really?
Kind of lived the whole semiconductor.
Where did you
cycle.
start?
I was in Motorola and Cadence and
Excellent.
Genesis,
Excellent.
but the story I used to say is never say never in this industry.
Hmm.
You always find a solution, so the 1 micron barrier, the deep sub-micron barrier to the nanometers. And now, actually, you didn't get into it, but the packaging aspects
Yes.
of pulling together chiplets that you can combine chips from different technologies, stack them up. So yeah, maybe the silicon will eventually peter out in terms of how much you can scale. But the scaling is expanded to a different scale where you just, I don't think there's any bound to how much chips you get, but how many transistors you can get in a packaged device.
You're right, that has always been the attitude, I don't care what the problem is, give me enough money, I can solve it. By the way, I talked to Joe Costello a couple of weeks ago, he worked for me, so, and what he said he would. I think we ought to let these people out, do some real work.
Thanks again, John. This is amazing.